So can you give me a rule for determining whether or not it will fit in a 3-digit hex number? Three digits or fewer, yes, and the right sign, i.e. positive to go forward, negative to go backwards. Okay. So this won't do. PC relative is out. So now we're going to do base relative. So how does that go? Destination minus base, right? Destination minus base. So beta 2119. What's base?
2116.
Like so. Yes? Okay. So we now have 1, 2, 4, 0, 0, 3. One, 2, 4, 0, 0, 3. Everybody got it? Okay. STA alpha. STA. Okay. So STA, let's see here, is STA is 0C. Zero C. Okay. So, base or PC relative? That's the question. We've got STA alpha. So the destination minus source plus 2. 3 rather. Yes? Is that right? What's the source? STA alpha plus 3. Is that right? Somebody who says no, what's it supposed to be? Not sure, just thought of it. Okay. I think it's right. Does it work? No, it's too big. It will not fit in 3 hex digits, so PC is off the table. It must be base relative. Okay, so we're going to 2116. Still, that hasn't changed, and we are going to subtract that from, and what is? Sorry. Can that be right?
Yes.
So what's our number then? 0 F 4. The displacement's 0. Is that right?
Yes.
Okay. Yes, it's how far forward from alpha do we go? Well, not very far. Okay, add data. Last one. Okay. Add data. So add is 1/8. then all right, let's try PC relative. The destination is data. And what's the source plus 3? Oh dear. Is that right? And then this is 1 B2. Is that it? Good. All right. Object machine code for data. What goes there?
Where's Jules
Okay. Buff, what goes there?
Nothing.
What is it?
Nothing.
Nothing. Alpha?
5
Okay, 5 zeros. The beta?
Same.
Same thing. Okay. So I hope you have found this helpful. I said I don't want to have, a D average over midterm. That would not be cool. So I just wanted to go through this real quick. So how are the programs coming? About done? No? Okay, persevere. Do you have questions? Some interesting questions that people have asked me. One is, how do you deal with the parameters? When do you discover or come up with the official quote-unquote list of parameters for a macro? There's nothing in the signature, it just says name macro, but there's no signature provided. So how do you get the signature? Anybody? What do you do? Ask questions, okay. Well, let me suggest this to you. Suppose there's a \1 and a \2 in the macro definition. But I call the macro with 3 parameters. What should it do? Yes?
So when I did that, I just ignored the \3.
Okay.
Didn't use it.
I think that's acceptable behavior. You just don't use it. I think that's acceptable behavior. If you have detected an extra parameter, done something about it, that's good, but it's not 100% necessary. We're just getting more. And I know the way the existing preprocessor works. I haven't tried passing too many parameters. But if you don't pass enough, then you get an empty string substituted in. And so, you will see an instruction that might look, I don't know, something like this. So then, when the assembler gets that, it errors out. It's an invalid syntax. Should it be caught at the macro level? Well, it's commonly not. That's the point. It's not necessary. Because it wouldn't slip through and give you wrong code. That would never happen. So what I suggest you do is at the point of invocation, that's when you grab the macros, the parameters. During definition, it wasn't really necessary. During expansion, it's critical. That's the point where you have to do something with them. And you can use any structure you want to, but I suggest a vector because the vector has a size method that makes it super easy. So then, if I call a macro foo, D1, D2, A3. So then the vector at index 1, 2, and 3, which makes it really easy to do the substitutions. This is all the backslash 1s. This, the backslash 3, so the index is the parameter number. And if there's a 0, you can put a null there or just not do anything with it, but an empty string would be fine. That way, if you have dot, it'll error out. If somebody provided a size here, then that would be, of course, backslash 0. Questions? Okay, so this isn't terrible. I suggest you store your macros if you have it in a map. A map because it's easy. You have one container structure that holds all of the stuff, the symbol table, the lines of code, for instance, the invocation counter, and so on. You have a struct that holds all that. That's the value, and the key is the name of the macro, which makes it super easy. Other questions? Anyone? Yes?
So I had a problem when I was storing the macro. If it had a size, it would store it twice. Because one of them would be dot .b, for example, and the other one would be itself. So like, let's say, for example, to upper.
Okay, well what you should store is just to upper. And so the backslash 0, if there is one, would take care of the size. If the programmer that's writing the macro put backslash 0 in the macro definition, and there isn't one, then it would be missing. And you would get this result. But you shouldn't have two macros, one with a dot and one with not, or something like that. You don't want one. You don't want two definitions for the same macro. Other questions? Anybody? Okay. Then we're going to move on and start talking about compilers. So, I like to cherry pick from this chapter because we have a class in compiler construction. It hasn't been offered for a while, but I expect it will be very soon. So, what does a compiler have to do? What does a compiler do that an assembler doesn't do? How about the output? The output from assembler versus a compiler, is it the same? Okay, what is an assembler output? You run the assembler on a file, what does it produce? Object code. You run a compiler on a source code file, and what does it produce? Object code. The same thing. Now, they may not be the same set of instructions, but essentially, the output for both, in both cases, is object code. And the only question is how you get there. So compilers process a sequence of tokens. It's useful to think of tokens as the elements of the language. And what might a token be? Keyword. Things like for, do, while, if. Keywords that are essential parts of the language. Variable names. Method names. Class names. Numbers. Strings. Operators. And then things like parentheses and brackets. Things like that. So there are three components to a compiler here, three main components. First, you have a scanner. Then you have a parser. And three, you have object code generation. So we can roughly divide the activities into these three sections. So the scanner, what does a scanner do? It identifies the type of each token. What is it? Is it a keyword in the language? Is it a variable? Is it a class name? The parser then identifies each statement. And it does a syntactic analysis. Based on rules, based on the grammar. And finally, the code generation translates each statement. Is converted to objects. So what is a grammar? What is a grammar? What does that mean? When we refer to computer languages as languages, but are they really? How is Java like French? Not many people know it. That's good. All right. So, and I mean, in what sense are programming languages actually languages? And the answer is they have grammars, they have rules, a set of rules about what's allowed and what is not allowed. And so every statement in the language has to fit with the set of formal rules. And these are defined a number of different ways, but the most common is perhaps the Bacchus-Nauer form. So there are two parts to this. The first is the set of rules, and the second is the syntax or the semantics of it. So imagine that we have this in Java. Let's say Java. And okay. Are those statements both valid? Do they do the same thing? They don't perform the same operation, do they? But what does B plus C mean? It means concatenation, but the integers is very different. It's addition. All right, so there's a rule. This is allowed, but the meaning differs, and that's the idea of semantics. So these are generally expressed in a set of rules. So the grammar exists as a set of rules, and they try to be unambiguous. There are always cases where you can come up with ambiguities, but they endeavor to be. So most common way this is done is with Bacchus-Nauer form. B and F. And so the rules take the form of a term equals some expression here, what's allowed. So some terminology. Non-terminal. A non-terminal is an expression that's in angle brackets and can be replaced by a collection of tokens. Then we have alternation. And these are the various forms that are available. Cat, or dog. Replacement. And that's the double colon equals. And it is simply an assignment. And then we have terminals, which are not replaceable. Or they are atomic in that sense. So I'm not going to force you guys to memorize a bunch of this, but I thought we could do an easy English sentence, and this translates exactly to computer code, but you'll get the sense of it. Okay, so the dog bites a man. So a sentence is a subject predicate. So that's what makes up a sentence. These are legal for a sentence as a subject and a predicate. Well, what's a subject? Okay, a subject. An article and a noun. And then what's a predicate? And the predicate is a verb and a direct object. And a direct object. Which is an article and a noun. So what you're trying to do is come up with a list of everything that's legal. It's obviously easier to do this for Java than it is for English. You get the drift of it here. An article is a and noun and lights. So this is just a simple way to show you how this goes. This Buffett form, you have these definitions. So this describes the form that an expression or a statement can take. Questions so far? Okay. Yes.
Oh, besides the second thing after non-German.
Where are you looking?
The second line.
Alternation. This?
Yeah.
Alternation. Or. This or that. So I'm not going to give you a bunch of rules on the file and ask you to analyze it. I find it tedious, but I'm after the main principles. I do want to talk about token recognition because this is really quite interesting. And it's often modeled on finite automata. Did you guys had automata theory? Yes, I think I'd rather take a beating than sit through a long class in automata theory, but it turns out that it's really useful for some things. So here's the scenario. Imagine that we have labels. And labels have to start with the letter, but they can't start with the number, but they can have numbers in them. So we want to come up with a model of what that could look like. So we have automata that's used for these, and that's states and the transitions between them. So finite automata means a fixed number of states that exist and the transitions between them. So for you have an entry point, and then you have directed graph essentially. Something like that. So you go from state to state. So as you enter, the first thing, the only thing you can have is A through Z period. But once you're there, you go to 2, and 2 is either terminal, or you can loop back around and have A through Z, 0 through 9. So I'll write another one here, and let's look at it. Go to 1, and 1 goes to 2, 2 goes to entry. 324, which is the terminal. Then we have A, and then B, and then C, and then we can go back here. This is A, and then on 4, we can have a nice little loop. This is C. All right. Valid or invalid? So can you find your way through it and get this? So you go to A, well, it's got to start with an A. Different question. And then can we get a B? Yes. Can we get a C? Yep, it works. And that's the terminal. Okay, what about a C? How do you get from A to C? You can't. A always goes to B, so you have to have A, B. Anything else is impossible. Okay, you have to have B, A, B, A, C. What about that? Yes, no, baby?
No.
Not valid. No way to get there. Exactly. A, B, C, A, B.
Yes.
Yes.
Yes. Well, I have a question. What about that terminal? Well, it needs to terminate in the terminal.
So it needs to end in a C.
So there you go. Yeah. So this is a way to qualify how these tokens ought to look. And how you can actually check those weird things. So they can model this as a finite state automaton that check tokens this way. It's kind of a cool idea, isn't it? Another important idea. And that would be, how does the computer, how does the compiler handle expressions? Arithmetic expressions, let's say. So let's imagine that we have this, 2, 3, 4 plus 5 plus 6 minus 2. Okay, do match. 1, 2, 3, 4, 1, 2, 3, 4. So how is the computer supposed to process this? Given any expression, any valid expression, yes,
Doesn't it change it to
it is infix.
by a
It will change it to postfix or prefix. Usually postfix. Why? Why would it change it to, well, what is postfix? What does that mean? Postfix? Okay, exactly. Good, Tyler. Yeah, this is infix. This is what we're used to. A plus B. Postfix, prefix. Operator, operand, operand, or operand, operand, operator, that's pre and postfix. They both accomplish the same goal. Well, what's the goal? Why would you do that? Why would you change that to pre or postfix?
It's easier for the compiler or interpreter to understand.
Okay. Why?
It's just easier for the programmer to understand.
Well, what's wrong with infix? What's the problem with that. Order. Order of operations. The problem is the pesky parentheses. You wouldn't have to do anything special if you didn't have the parentheses, and what they do is they change the evaluation order. So if you convert to prefix or postfix, you can get rid of all of the parentheses, which makes it, easier to process and unambiguous. Can you give me an algorithm for processing that without converting it to prefix or postfix? Now imagine I said, okay, pop quiz. Everybody take out a piece of paper and give me an algorithm for processing this and coming up with the answer. How would you do it?
You find an open brace, don't calculate until you find, or an open parentheses, don't calculate until you find the open.
Yes.
Every time you find an open brackets, you pass the rest of this string as a recursive call of the same function until you find a closed bracket and you calculate what you found.
Oh, that sounds messy. It's probably about right, but messy. Yeah? Okay, I'll buy that. I have a suggestion. What do you think about this? Parse the string until you find a closed paren. Go down the string until you find a closed paren, and backtrack to the first open paren. Evaluate. Okay, if we did that, go through this thing until we either run off the end, there wasn't one, or we hit an end paren. There's the first one. Backtrack and grab the closest open paren. Now do 6 minus 2 and you get 4. Go again, you hit this, backtrack till you find the closest open paren, and 5 plus 4 is 9. Does that work? But it's messy. So it's easier to convert these things into pre or post fix. So what does this thing look like? Well, the prefix and postfix are operand, operand, operator, or operator, operand, operand. A, B, plus, plus, A, B. So as postfix, if we do this, what do we end up with? 2, 3, 4, 5, 6, 2 minus plus, plus, now how do you evaluate that? Yes. You can. That's the easiest way to do it, because what's hard with the computers going down and backtracking, but with the stack it's super easy. So okay, you find the first operator, minus, and take the 2 preceding things and you evaluate it. 6 minus 2, which is 4. You now have 2, 3, 4, 5, 4 plus plus times times. So you have 4 and 5 and a plus. And 4 plus, or 5 plus 4, of course, is 9. So you've got all of this taken care of now. So we have 4, 9 plus. 4, 9 plus. And that gives us, what, 13? And then we have 3 times 13, 39, and finally we have 2 times 2 times 39 is what? 78, and there's your answer. So this is easier than trying to process the parentheses. Just taking them out makes this much easier. Okay. One One of the things compilers do is optimize code. There are a number of ways this can happen. There are a number of techniques for code optimization. And so I want to mention some of the most common ones, and I'll expect you to know what they are. All right, what is strength reduction? This is where you substitute a cheaper instruction for a costly. If you have a 2 squared, power function costs something. Can you do 2 times 2 instead? Sure. Another common one. It turns out that, well, setting aside the function calls, i.e. power function and things like that, square root, just the built-in operators. The built-in operators, what's the most expensive? I.e. takes the most amount of work. Division? Modest division. Yes, division is the worst. And what's next to division? Yes, multiplication and division are the most expensive operations on pretty much any CPU. Why is that? What makes multiply or divide more expensive than add or subtract? More steps? Well, actually, it doesn't take a whole lot of thought to realize. Suppose I ask you to do the following. So we're just talking base 10 here, let's not do base 16 or 6. Okay, if I ask you to do this, would it take very long? A couple of seconds, right? Pretty easy. Is that going to take longer? A little bit longer, a lot longer?
For us,
A lot longer. Often. Yes. Often. So it's not different inside the machine at the level of the data paths in the CPU. The same amount of work has to get done, period. There's no magic secret recipe for multiplying that only computers know how to do. I remember years ago when I was in high school, this was the 70s, I have to admit, I graduated in 74, forever ago anyway. It was before the digital age. We didn't have calculators, so we used slide rules actually. But what I remember so distinctly is this high school bought an electric calculator. This was a big deal. I mean, it's the size of a suitcase. This electric not electronic calculator, it wasn't digital. It had gears in it and a motor. What was really cool about this machine was that it could multiply numbers, not just add and subtract, which has been around forever. You can have strictly mechanical ones with a pull handle to do add and subtract. That's no big deal. But multiply is a whole different story. So, this was marvelous. This is the reason why mathematicians use slide rules. Engineers, they use slide rules. Why? Because it's too hard to multiply and divide. So the nature of logarithms, you take the log of something, and what do you do with the exponents? You add them. So you have this problem from hell that you can't really do very easily. If you take the logs, you add them, and then you convert back, and that's how you multiply really big, big numbers. And that's why people use slide rules, because you add the logs. All right, so here was this great new machine, and it actually did multiplication, long multiplication and division, which was a marvel for its time. I still remember this. And I remember a bunch of us standing around watching this thing. Somebody punch in the numbers and hit the equals, right? You hear it going, it goes ka-chunk, 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 ka-chunk. It was like 30 seconds, ka-chunk, 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 ka-chunk. And finally it printed, spit out the number, and ooh, and isn't this marvelous? Well, okay, it seems ridiculous. Amazing anyone would be interested in such old stuff, but the point is the amount of work getting done is more measurable by a strict mechanical thing that's going ka-chunk, ka-chunk, ka-chunk. And it took a long time to multiply numbers. So you want to avoid making the computer multiply numbers where you can. It takes longer. Depends on the architecture, and of course they've gotten better at it over the years, but you still have the same amount of work getting done. All right, so what can you do? What would the compiler do? Change the instruction. If it's a power of 2, you can shift instead of multiply. Not that you write shift by 1 bit, that's equivalent to multiplying by 2. Is everybody, that you should know this for 2/3. All right, so strength reduction involves changing a more costly operation for a cheaper one. Common sub-expression elimination. Or y less than count over 2 plus do something. Now, if this is executed the way it's written, how many times are you going to divide count by 2? With every pass in the loop, you're going to divide count by 2 and check it, right? So if it's going to loop 1,000,000 times, how many times are you going to divide count by 2? 1,000,000. And are you going to ever get a different result? No, it's the same every single time. Count over 2. So the compiler says, wait, he's been drinking again. And 10 equals count over 2. And of course, go one better and do right shift. Same thing as divide by 2 is a right shift. And then here, instead of count over 2, what do we have? We have 10. So we calculate it one time instead of a million times. Is that better? Sure it is. Yes. All right. Dead code pruning. Well, sometimes you have unreachable code for one reason or another. What's a good example of unreachable code? Something after a return, or an if-else block that's impossible. Yeah, that's less than or equal to 0. Do something else. Yeah, x is greater than 0. Do something else. Do a bunch of things. Well, if x is not less than or equal 0, and x is not greater than 0, then what are you going to execute the else part? Give me a number that's not less than, greater than, or equal to 0. I don't think there is such a thing. All right, so the compiler, in some cases, it depends on the expression. The compiler will look at this and see, what can I take out? What can't be reached? And they're actually pretty good at telling you that. You have, unreachable code. All right, that's dead code. Loop unrolling. Well, what difference does it make? Loop unrolling means removing the loop. So imagine that I have an array, and I want to set it to 0. I've been using it for something, and now I want it to be 0. Okay, how many instructions execute for each pass of the loop? Well, the I equals 0 is an initialization that's a one-shot deal that happens first. Once you have that, what are the steps?
Steps out of the loop, you mean?
What are the steps that happen? And you look at me, what, there's only one thing in the loop. No. So let's write pseudo 4. Yeah. I is greater than or equal to 10. Go to 10. Right? Then array I gets 0. I plus plus. Go to 4. And then down here is done. This is what happens with each pass of the loop. The compiler will remove a for loop and put this in its place, because the CPU doesn't know anything about any for loop. There's no machined instruction that corresponds to a for loop. They are essentially while loops, that's all it is. It's just a while loop with a little bit of syntactic sugar attached to it. So the first instruction, the if, is actually two things in machine code. It's a comparison and a branch instruction. Branch if you're done. So that's 2. And then we have array I equals 0, 3, I plus plus 4. Go to 4, that's 5 instructions for every pass of the loop. So you got one assignment with 5 instructions. So only one of those 5 instructions actually does anything useful for you. So there's a lot of overhead. So what the compiler in these cases will do is this. So if you have 5,000 passes of the loop, you'll get 5,000 instructions inserted. Well, no human programmer would ever do that. But the compiler will take the loop out and just have sequential instructions like this. Is it faster? Yes. Is it noticeably faster? Yes. Yes, it's the overhead, 4/5 of what the computer's doing is overhead. So by removing that, you can have a great improvement in performance. So that's called loop unrolling. Okay, so we'll stop there for now. Wednesday. What's Wednesday? The test. I know you can't wait. I know you can't.